Good evening. Welcome to the second video on problems on electrostatics. So in the first video we have seen a particular problem where we have two charges and we want to find out the force on a third charge as a vector sum of those two forces on the particular charge, and we need to find out the net electric field on the test charge due to the first given two charges. So those kind of problems may be asked in the university exams. The second type of problems may be from the sheet of charges. There can be line charge, there can be sheet charges, that is the surface charges. Third may be as volume charges. So those kind of problems may also be asked in the university exams. So as of that, we are also going to see a problem on finite sheet charge, a finite sheet of x which is spread over 0 to 1, y which is spread over 0 to 1 on z is equal to 0 plane has a charge density of rho s is equal to xy into x square plus y square plus 25 power 3 by 2 nano coulomb per meter square. So coulomb per meter square has been given. So this is the sheet charge or a surface charge. So you have to find out what is the total charge on the sheet. Second one is the electric field at 0, 0, 5. So this third we can neglect now for now. So we need to find out these two things, the total charge on the sheet, and we need to find out what is the electric field at a given point. So what is the formula for finding out the total charge? Because we have been given with the sheet's dimension which is located at z is equal to 0, so we will be having only two dimensions. So we can define that particular sheet charge with the two dimensions. That's how we are going to find out the differential surface. So in order to find out the charge, the total charge on that particular sheet can be found out. Q is equal to surface integration of rho s into ds. So this is a formula we know already. What we have to find out is, we have to find out what is this particular ds. So ds can be found out from the data given. This sheet is spread over x, which is spread over from 0 to 1, on y is spread over 0 to 1. So we need to find out this differential surfaces dx into dy. So the integral values are going to vary from x is equal to 0 to 1, y is equal to 0 to 1. This rho s value has been substituted. You have to find out what is this particular integral value. So how to find out this integral value? Because we are having xy is being multiplied with the complex term x square plus y square plus 25 power 3 by 2. So we cannot find out it directly. So how we are going to deal is, we are going to change this dx as df x square. So if you want to replace this dx with the df x square, then you need to find out what is the value of this df x square. So what is df x square, which is equal to, if you differentiate x square, then 2x into dx will be coming. So this x into dx has been already noticed in this particular equation. So x into dx has been noticed. So we can replace this x into dx as df of x square into 1 by 2. So what if you change this differential value, then we need to change the limits value also. But limits value are very simple because it is from 0 to 1. So if you substitute 0 to 1 for this x square, will also result in x is equal to 0, x is equal to 1. So x square will also be 0, x square will also be 1. So our limits are not going to change. So 0 to 1, 0 to 1. 1 by 2, just take it out. Then we will be having the remaining terms as y into x square plus y square plus 25 over 3 by 2 d of x square dy. So if you integrate with respect to x square, then we will be getting y into x square plus y square power plus 25 power 3 by 2 plus 1 divided by 3 by 2 plus 1. So what is 3 by 2 plus 1, which is 5 by 2. So power 5 by 2 divided by 5 by 2. We will also have to differentiate this with respect to x square. So if you differentiate these terms, it will be 0. Then if you differentiate with respect to d of x square, then we will be getting the value of 1. Just apply the limits. So if you apply the limits, then we will be getting the value of, you can make this 5 by 2 as the into 2 by 5. Limits will be applied, so you will be getting this value as y into y square plus 26 power 5 by 2 minus, if you apply 0, then y square plus 25 power 5 by 2 d of y. Here also terms are somehow complicated. How x square y square term is inside the power term. Here also y square term is inside the power term. So if you want to integrate this directly, it is not possible. So we have to again substitute y square as d of y square, as we have done in the previous case. So you are going to apply d of y square is equal to 2y dy. So y into dy is already exist. So we can replace y into dy as 1 by 2 d of y square. The limits may not be going to vary, as we have seen in the previous case. Y square will also be 0, y square will also be 1 as upper limit. So if you apply the lower and upper limits, and if you integrate the remaining terms, you will be getting y square plus 26 power 7 by 2, because 5 by 2 plus 1 is going to be 7 by 2 by 7 by 2 minus, if you integrate this term, then y square plus 25 power 7 by 2 divided by 7 by 2. The integration limits are 0 to 1. So if you substitute the value, then you can write this particular terms as like this. And if you apply the terms, you can take this 7 by 1 divided by 7 by 2 as 2 divided by 7. So if you apply 1 as a first upper limit, then this term will be 27 power 7 by 2 minus 26, that is 1 plus 25 is 26, 26 power 7 by 2 minus, again if you want to apply this 0, then 26 power 7 by 2, apply 0 over here, so 25 power 7 by 2. So if you simplify, you will be getting the Q value as 33.15 nanocoulomb, because our first given rho s value is nanocoulomb per meter square, so our Q will also be nanocoulomb. So we have find out what is Q. So first division is found out. Next division is going to be electric field at 0, 0, 5. So how to find out that particular value? You have to find out the electric field due to the surface charge. So the surface charge electric field formula is going to be E vector is equal to integration of the surface integration of rho s ds divided by 4 pi epsilon naught r square into ar cap. Also we can write this as rho s ds divided by 4 pi epsilon naught r cube. In the upper side we will be having r vector. So what is r vector? We have to find out the distance between this particular point 0, 0, 5 to this particular sheet of charge. So we can find the r vector as 0, 0, 5 minus, because this particular point we don't know, so we have to take it as a x plus y plus 0. Why it is 0? Because we are having z is equal to 0 as the place of this particular sheet of charge. And also we are having the spread of the sheet of charge only. We don't have any of the point values. So that we are going to represent this particular term as a x and the y term as a y. So if you manipulate this particular value, then we will be having minus x into axy minus y into ay cap plus 5 az cap. So if you substitute these values in this particular formula, then rho s is equal rho s is xy of x square plus y square plus 25 power 3 by 2. ds value r vector is this particular value. Substitute. What is ds? It is dx into dy divided by 4 pi epsilon naught, the value of this, the magnitude value of this particular vector. So what is the magnitude value? Which is x square plus y square plus 5 square power 3 root. You have to take the root. Also we can write this particular term as x square plus y square plus 25 power 3 by 2. So if you have this particular term, these two terms are equal, so you can cut them. Also we know what is 1 divided by 4 pi epsilon naught, which is 9 into 10 power 9. You can apply the integration value limits as 0 to 1, 0 to 1 for x and y. And if you multiply this xy term into this particular vector term, you will be getting minus x square y dx dy ax cap minus x y square dx dy ay cap plus 5 xy az cap dx dy. So if you integrate with respect to the each and every terms, first you just integrate with respect to x. So in the first term, minus y x square dx is there. So if you integrate x cube divided by 3, apply the limits 0 to 1 dy ax cap minus, if you take y square, then y square as the constant, then y square integration of x into dx. So x into dx is x square by 2, limit apply 0 to 1 into dy, because we are having two integrations, so one integration is remaining now, so 0 to 1. Also if you integrate this term, x into dx is, can be integrated, others are going to be constants, so 0 to 1 5y x square by 2, because we are going to integrate x into dx, so x square by 2, limits are going to be applied from 0 to 1 dy az cap. Now if you apply the limits, and if you integrate 0 to 1, then you can integrate like if you apply the value 1 by 3 will be the answer, so minus 1 by 3. If you integrate y dy, then you can write it as y square by 2, because I have skipped one step here. That is not a problem, because we can find out the limits value very easily, so that only I have skipped that particular step. So minus 1 by 3 y square by 2 0 to 1 x cap minus, so if you apply the limit over here, it is 1 by 2, so minus 1 by 2 y cube dy is here. So if you integrate y cube y square dy is here, so if you integrate, it is y cube divided by 3, limits applied from 0 to 1 a y cap plus, if you apply the limits, so 1 by 2 will be there, so 5 into 1 by 2 is 5 by 2. If you integrate y into dy, then you will be getting y square by 2, 0 to 1 a is at cap. So if you apply the limits again, you will be getting the value of 1 by 3 into 1 by 2, so you can write it as minus 1 by 6 ax cap, 1 by 2 into 1 by 3, so you can also write it as minus 1 by 6 ay cap, 5 by 2 is here, so if you apply 1, then 5 by 4 will be coming. These 0 limits will going to only give the 0 values, so we are neglecting those limits. So if you simplify this term, then you will be getting this value. So if you are going to multiply this 9 into 10 power 9 inside this particular vector value, so you will be getting into 10 power 9 volt per meter. You can also write this 10 power 9 as kilo mega tera, like tera will be coming, so tera volt per meter will be the answer for this particular question. Thank you.